Welcome to Deep Research TV, where we dive deep into the most fascinating mysteries of science and the universe. Have you ever looked up at the night sky and wondered how satellites stay up there without falling back to Earth? We launch these massive chunks of metal into space, and somehow, they just keep circling our planet for years, sending us GPS signals, TV broadcasts, weather forecasts, and even letting us video call across continents. But Earth's gravity is constantly pulling everything toward the ground. So why don't satellites crash down like a thrown ball eventually does? Is there some invisible force holding them up? Today, we're going to uncover the real science behind it based on Newton's laws, orbital mechanics, and real-world examples. Let's break it down step by step. First, the common misconception. Many people think satellites are above gravity or floating in zero-gravity space, far away from Earth's pull. That's not true. Gravity doesn't just stop at a certain height. In fact, satellites in low Earth orbit about 200 to 2000 kilometers up still feel around 90% of the gravity we experience on the surface. The International Space Station, for example, orbits at about 400 kilometers altitude, and gravity there is still strong enough that, if it stopped moving, it would fall straight back to Earth in minutes. So, if gravity is pulling them down, what keeps them up? The answer is speed. Satellites are moving sideways incredibly fast enough that as they fall toward Earth, the planet curves away beneath them at exactly the same rate. They're in a constant state of free fall. But they never hit the ground, because Earth is round. This idea goes back to Isaac Newton in the 17th century. Newton imagined a cannon on a very tall mountain firing a cannonball horizontally. If you fire it slowly, it falls in a parabolic arc and hits the ground nearby. Fire it faster, and it travels farther before hitting. Newton realized that if you could fire it fast enough, about 7.9 kilometers per second, the cannonball would fall toward Earth at the same rate that Earth's surface curves away. It would keep missing the ground forever, orbiting the planet. That speed is called orbital velocity, and it's the key to staying in space. For low Earth orbit, like the ISS, satellites need to travel at around 28,000 kilometers per hour. Nearly 8 kilometers per second. At that speed, they complete one full orbit every 90 minutes or so. The ISS does about 16 orbits per day. Because they're always falling but moving forward so quickly, they stay at a constant altitude. But not all satellites orbit at the same height or speed. There are different types of orbits. Geostationary satellites, like the ones that beamed your satellite TV, sit much higher, about 36,000 kilometers above the equator. At that exact altitude, their orbital speed matches Earth's rotation period of 24 hours. So they hover over the same spot on the ground, appearing stationary from our perspective. Their orbital velocity is slower, about 3 kilometers per second, but the weaker gravity at that distance balances perfectly with the centrifugal tendency to fly outward. This balance is crucial. In orbital mechanics, there's no centrifugal force pushing out in the classical sense. It's actually straight-line inertia, Newton's first law. The satellite wants to fly off in a straight line due to its momentum, but gravity constantly bends that path into a circle or ellipse. The two forces balance. Gravity provides the centripetal acceleration needed for circular motion, while the satellite's velocity provides the outward tendency. It's like swinging a ball on a string. The string gravity pulls inward, and the motion keeps it from collapsing or flying away. Real-world proof. Over 10,000 satellites are currently active, with thousands more in graveyard orbits or deorbited. The first one, Sputnik 2, launched by the Soviet Union in 1957, orbited for months before atmospheric drag eventually slowed it down and caused it to burn up. Modern satellites in higher orbits can last decades because there is almost no air resistance to slow them. But what about drag? In low Earth orbit, there's still a tiny bit of atmosphere in traces of gas molecules. Over time, this creates drag, slowing satellites and lowering their orbit. That's why the ISS needs periodic boosts from thrusters to maintain altitude. About 100 meters per day is lost without correction. SpaceX's Starlink satellites, for example, are designed to deorbit safely after their mission by lowering themselves into the atmosphere to burn up. Higher up, in medium or geostationary orbits, drag is negligible, so satellites can stay stable for 15 years or more. GPS satellites orbit at about 20,000 kilometers in medium Earth orbit, completing 2 orbits per day with extreme precision. Their clocks even run slightly faster due to weaker gravity, requiring relativity corrections. just like we discussed in time travel videos. What if a satellite stops moving? Without velocity, it falls straight down. That's why launch rockets don't just go straight up, they accelerate sideways to reach orbital speed. The Falcon 9, for instance, burns most of its fuel, achieving that horizontal velocity, not just height. There's also the problem of space debris. Defunct satellites and fragments orbit at the same speeds, creating risks of collisions. The Kessler Syndrome, where one collision creates more debris, leading to a cascade. That's why agencies track over 30,000 objects and plan maneuvers to avoid hits. Future satellites will use ion thrusters for efficient station keeping, electric sails, or even magnetic interactions with Earth's field. Mega constellations like Starlink aim for thousands more, but with better deorbit tech to keep space clean. So, satellites don't float or escape gravity, they master it. They fall endlessly around Earth, perfectly balanced by their blistering speed. It's one of the most elegant demonstrations of physics in action, turning a destructive force gravity into a stable orbit that powers our modern world. What blows your mind most about this? The sheer speed needed, or how it all traces back to Newton's thought experiment? Let us know in the comments. Smash that like button if you learned something new, and subscribe to Deep Research TV for more deep dives into science and space. Until next time, keep looking up.